How close are we to artificial general intelligence, AGI for short? At the end of last year, OpenAI announced their newest model, o3. That caused quite some buzz and a lot of speculation that we're close to machines with human-level intelligence. If you trust YouTubers, which maybe, just maybe you shouldn't, o3 is AGI. Let's have a look. The newest OpenAI model impressed with several test scores. First, there is a test with hard maths problems called Epoch AI Frontier Math. It'd probably take me a year or so to figure out what the questions even mean. So far, the best an AI did on this test was to correctly solve 2% of the problems. o3 managed a whopping 25%. The second impressive feature is that it produces code faster and with less compute, so at a lower cost than previous models.
It's like for an order of magnitude more speed and cost, we can deliver the same code performance on this
or even better.
Or even better.
If you're a software developer, this is either very good news or very bad news. And the third test score, which has attracted most of the attention, is o3's performance on a test called ARC-AGI. That stands for Abstract and Reasoning Corpus for Artificial General Intelligence. It's made of graphical puzzles. Here is an example of an input and an output, another one, and another one. And then here is the question. You can almost certainly solve this, and if not, the problem is probably your glasses and not your brain. Yet AI struggles with inferring the logic behind these questions. Before the o3 announcement, the record holder for this test scored about 55%. o3 scored 75% at low compute and 87% at high compute, though they paid a price for that, literally. The high compute version cost as much as $3,000 for a single task, whereas the previous model made do with a few dollars. Speaking of cost, the Chinese firm DeepSeek just released a new open source model that has a similar performance to GPT-4. It was vastly cheaper, but has an interesting identity problem.
Now, I've been testing it out this morning, and on the surface, it looks and acts just like OpenAI's ChatGPT. And in fact, it actually thinks it is ChatGPT. When I asked, what model are you? It answered, I'm an AI language model created by OpenAI, specifically based on the GPT-4 architecture.
But back to o3. On the technical side, the biggest advancement of o3 is that it internally produces several possible solution paths and then evaluates them. This is called a chain of thought. It can even keep track of which solution strategies work best. The high score on the ARC test attracted attention because the average human score on this test is roughly 76%, so that's comparable to the o3 performance. But it's not like passing this test means you have an AGI. It's that if you have an AGI, it should pass the test. So no, this result does not tell us that o3 is AGI. Still, Stephen Heidel from OpenAI commented on X Twitter that it's beginning to look a lot like AGI. Part of the problem is that we don't have any good definition for what AGI even means. Indeed, Sam Altman, the CEO of OpenAI, says he doesn't like the term, but he thinks that by the end of 2025, machines will outsmart humans in many ways.
People would be sad if I didn't ask you. We hear a lot about artificial general intelligence. What is it? When is it going to happen? And what will be the implications?
It used to be a term that people used a lot, and it was this really smart AI that was very far off in the future.
Yeah.
As we get closer to it, I think it's become a less useful term. People use it to mean very different things. Some people use it to mean something that's not that different than O1, and some people use it to mean true superintelligence, something smarter than like all of humanity put together. But I will say, by the end of next year, end of 25, I expect we will have systems that can do truly astonishing cognitive tasks, like where you'll use it and be like, that thing is smarter than me at a lot of hard problems.
Though the reason he doesn't like talking about AGI may be that OpenAI has a lucrative deal with Microsoft that, however, has a clause saying the contract will terminate if OpenAI reaches AGI. They did this in 2019 to prevent commercial abuse of the technology because safety and all, but come 2024, they'd prefer removing the clause because fuck safety. Personally, I strongly doubt that OpenAI will make it to AGI anytime soon, if ever. It's because the test results alone don't tell the full story. O3 is still a specific type of AI called a large language model that's trained on a lot of data with examples of the problems it's supposed to solve. But most humans can solve the ARC problems without having ever seen anything like it before. This tells us that these models are not remotely comparable to human intelligence. Many in the AI business currently think that large language models will scale with more data. That is, the more data you feed into them, the better they'll get, eventually surpassing human intelligence. This scaling hypothesis has been observed in many previous models. However, as we just discussed in an earlier episode, there are indications that progress on LLMs has slowed down and that these models will not continue to scale. Yann LeCun from Meta is among those who think that large language models are not the way to AGI, and he thinks it won't come before the end of the decade.
You know, we have LLMs that can pass the bar exam, so they must be smart. But then they can't learn to drive in 20 hours like any 17-year-old. They can't learn to clear up the dinner table and fill up the dishwasher like any 10-year-old can learn in one shot. Why is that? Like, you know, what are we missing? What type of learning or reasoning architecture or whatever are we missing?
It's not going to happen next year. Like, you might have heard from you know, some other folks.
Sam Altman, hopefully.
Sam Altman, you know, Elon Musk, you know, various people, or you know, Dario Amodei. It's going to happen within the next 2 years or something. No, what may happen in the next 2 years is that it's going to be more and more difficult to find cases where common people will be able to ask questions to the latest chatbot that the chatbot would not be able to answer.
Gary Marcus, a cognitive scientist who's worked on the emergence of intelligence, also thinks that AGI is much harder to achieve than many in the field presently believe, and that the problem's made worse by the intellectual monoculture of Silicon Valley.
AI is harder than its originators realized. And actually, I should have added, it's harder than most of the people who are hyping the field right now realize, which includes CEOs of companies like OpenAI, not to mention any names. We have an intellectual monoculture in which almost all of the research dollars and energy goes towards transformer models and almost nothing else. And that's insane.
But OpenAI and Anthropic and others have spent hundreds of millions of dollars to train these models. They can't just start over again. It's too expensive. This makes it easy to predict what will happen next. These companies will quietly drop the AGI idea and instead find niches in which their models perform well enough to be profitable. Indeed, according to Business Insider, in internal documents between Microsoft and OpenAI, they define AGI as any system that will make more than $100 billion in profit. If I now tell you that OpenAI also considers putting adverts on its models, it suddenly all makes sense. General intelligence means spamming your customers with ads. The future will be bright. String theory, our best hope for a theory of everything, has been criticized for being impossible to falsify. But a group of string theorists now says that this isn't so. They just came out with a paper titled How to Falsify String Theory at a Collider. Well, that sounds like fun. Let's have a look. String theory as a theory of everything should contain all the elementary particles that we have already observed and that we collect in the standard model of particle physics. These particles are not all independent of each other. They're related by symmetry transformations that we collect in groups called U1, SU2, and SU3. No, wait, don't leave. I swear you don't need to know exactly what that means. Just that the numbers in the group names tell you the size of the group. The smaller the number, the smaller the group. As you can tell, the real world seems to make use only of very small symmetry groups. This brings us to the new paper. In string theory, one strictly speaking doesn't have particles. Everything is made of strings. It's just that some of those strings resemble particles. But they still must be related by these symmetry groups to correctly reproduce the standard model. No one so far found a way to exactly reproduce the standard model from string theory. However, string theorists have found a lot of similar models. And once you have these models, you can calculate how many particles should appear together in sets at a collider. These sets of particles are called multiplets. The quarks in the standard model, for example, form a triplet. The authors of the new paper now say, let's conjecture that particle models derived from string theory only have small sets of particles, so small multiplets. I doubt that this is correct, but let's just go with it. Then, so they say, we should never find a large set of new particles related by a symmetry group with a large number. So if a particle collider found evidence for something like that, this could rule out string theory. Well, this is just nonsense. Let's say I have a theory according to which the Large Hadron Collider will not produce unicorns. If it does produce unicorns, that'll rule out my theory. Therefore, unicorn theory is great. That's the logical equivalent of their argument, except that they covered their nonsense up with maths, distributed it over 30 pages, ran a computer simulation to go with it, and got paid for doing all that by the US Department of Energy. Though I have to give it to them, they invented an entirely new sort of nonsense. You see, the normal nonsense in the field is to invent new unnecessary things, claim that they make predictions which can be ruled out, and then pretend it's great if they're ruled out. The authors of the new paper, on the other hand, invent unnecessary things, claim there's something they don't predict, and then they pretend it's great if we don't see what they don't predict. Imagine the potential. No longer do you need a theory that predicts something new. It's sufficient to predict nothing new, which you could just have done by sticking with the standard model. You might think that this is a particularly extreme example of physics gone wrong by a basic misunderstanding of how science works, but in the foundations of physics, this is unfortunately the rule rather than the exception. To just give you two other recent examples, take the paper that made headlines with the title, "Dark Matter May Have Existed Before the Big Bang." If you look at the paper, you'll see that the lead author is the same person who claimed last week that dark matter was produced in a second Big Bang after the first two ideas that directly contradict each other. This isn't all that uncommon in this field. You can just make up some new maths, calculate some things, and publish a new paper. The stunning thing about this is that it doesn't even occur to them that this isn't how science works. This research was funded by the Swedish Research Council and also by the DOE. Another paper which I read last week, hoping it'd be interesting enough to talk about, is about a pixelated universe, something with dark energy, a top-down string theory construction. It's the classical example of adding unnecessary assumptions that don't solve any problem and then making predictions to claim that it's science because it can be falsified. This was financed by the NSF and the DOE. Most of this paper production in the foundations of physics stems from a very basic misunderstanding of the philosophy of science, is that they think it's sufficient for a theory to be falsifiable. But just being falsifiable doesn't make a theory scientific. Most importantly, a scientific theory should not make unnecessary assumptions, like particles are made of strings, or dark energy is pixelated, or maybe God made it so, but then I repeat myself. Now look, I'm not saying that everything in the foundations of physics is nonsense. I'm trying hard to find some interesting things to highlight in my science news. But damn, it is hard. The New York Times recently wrote that scrubbing carbon from the sky is the new climate gold rush. Gold rush, really? I'm very skeptical, but let's have a look. The supposed gold rush is a technology known as carbon dioxide removal. That's anything which reduces the amount of carbon dioxide in the air. The New York Times article summarizes the many recent investments into startups pursuing these technologies. To date, they make up about $5 billion that went into startups. The investments are backed, among others, by Bill Gates and Jeff Bezos, because who better to tackle carbon emissions than guys whose private jets have a carbon footprint the size of Luxembourg? The management consulting firm McKinsey estimates that the market for carbon dioxide removal will grow to a staggering $1.2 trillion by 2050. Trillion. That's the most remarkable turn of events. Carbon dioxide removal used to be a taboo topic. Environmentalists were arguing that it's just a ploy by the fossil fuel companies to encourage us to keep using their products, that it'd just cost a lot of money and distract us from better solutions. And that's basically correct, but it doesn't matter. The International Energy Agency concluded already in 2022 that reaching net zero by 2050 is virtually impossible without carbon dioxide removal. The IPCC too has found that carbon dioxide removal is part of all modeled scenarios that limit global warming to 2 degrees or lower by 2100. Environmentalists can now either admit that we have no chance to reach our climate goals or embrace carbon dioxide removal. And so the conversation about carbon dioxide removal has changed a lot in the past years. A recent study on how people discuss carbon dioxide removal in social media found that the frequency has markedly gone up and the sentiment has become increasingly positive. This is why I guess the New York Times speaks of a gold rush. It's the enthusiasm plus the forecast of substantial market growth. However, if you look at the stocks of some carbon dioxide removal ETFs or companies, there isn't much going on, and the status of carbon dioxide removal is way below the targets. This, for example, is a figure from the 2024 report on the status of carbon dioxide removal. On the left in dark grey, you see the approximate amount of carbon dioxide we currently remove. On the right in ochre, the amount we need to remove to reach the Paris goal. You might say that doesn't look too bad. It's just about a factor 3 or so. Yes, but look at this other figure. Almost all the currently existing carbon dioxide removal comes from reforestation or other land use changes. This contribution can't increase much because there's only so much land on Earth. It's just about 0.1% that's currently removed by new methods. It's those new methods that can scale and that need to be scaled by the year 2050 by more than a factor 1000. But wait, it gets worse. Almost all of the existing carbon dioxide removal that isn't reforestation is biocar and bioenergy with carbon capture and storage. Those are these ochre parts here. Both of those work by growing plants and then burning them without releasing the carbon. Those too are difficult to significantly scale up because they require a lot of land. The technologies that can scale are things like direct air capture, basically a way of filtering air, or seawater extraction, because seawater takes up the carbon dioxide from the air, or distributing minerals that absorb it, known as enhanced weathering. We talked about all of those in an earlier episode. The problems with these scalable methods is that at the moment they're hideously expensive. Estimates say that the cost of direct air capture needs to fall by at least a factor 10 for it to begin making commercial sense. McKinsey expects this to happen rather soon, but I am very skeptical. You see, once carbon dioxide is released into the atmosphere, it distributes and dilutes very quickly. Entropy increases. If you want to get it back out without taking up large areas of land, you need to reduce entropy a lot. That requires energy, and energy costs money. Another way to see the problem is this figure. Reducing costs will require further technology improvements. But while the amount of funding into carbon capture by grants has gone up in the past decade, the number of new inventions has gone down. Though you'll be thrilled to hear that, progress or not, the the number of publications has skyrocketed. At the moment, the excitement for carbon dioxide removal is based on pledges by big companies, including tech companies and multiple airlines. They say they'll buy carbon credits to offset their emissions. If the offsetting remains too expensive, the market will never come into existence. But what all this means is that we now have perfect conditions for a new economic bubble. Congratulations, humans. Well done. I recently learned from the BBC, out of all places, that a recent measurement of gravitational waves could be the first evidence for string theory. And not only that, it could also allow for time travel. If you think that sounds like a lot of nonsense, you're right. But there is a grain of truth in it, so let's go and dig it out. String theory says that the particles of the standard model, which we currently think are elementary, such as electrons, photons, and quarks, are really made of teeny tiny strings. They are too small for us to have observed them yet. But if these strings had been around in the early universe, some of them could have grown to huge proportions, the length of entire galaxies, but with basically zero width. These are known as cosmic strings. Cosmic strings are made of pure energy, and because they are so thin, their energy is highly concentrated. If cosmic strings existed, they'd leave several observable traces. One is that they'd act as gravitational lenses. Normally, gravitational lenses are created by galaxies or black holes, which create rings or parts of rings as an image. But because a cosmic string is a one-dimensional object, it'd very cleanly duplicate images behind it. Basically, one image goes left around the string, the other one right. There have been several candidates for lensing caused by cosmic strings, such as this one in 2006 that, however, turned out to be a pair of galaxies. Last year, I told you that astronomers have identified several more cosmic string candidates in data that was collected by the Planck satellite and that they followed up on with further observations at the Himalayan Chandra telescope. This way, they identified several candidates that seemed to be almost perfect image duplications and that could have been created by cosmic strings. These are now being further investigated. They might turn out to be pairs of galaxies too, but you never know. The BBC piece is about another way to find evidence for cosmic strings, which is that they create gravitational waves. That is because these long strings deform under the pull of gravity, which can cause kinks that can snap into a new configuration. This sudden reconfiguration emits gravitational waves at very long wavelengths. The news is now that an analysis has shown that this cosmic string gravitational wave spectrum fits very well to a tentative detection of gravitational waves in this very long wavelength regime done with a method called a pulsar timing array. For this method, one uses the timing of pulsars that are neutron stars which emit particle beams. They rotate, and so this particle beam reaches us with an extremely reliable period each time it points into our direction. If you measure distortions in the pulsar signals from different directions, that can tell you whether gravitational waves stretch the space in between, and they indeed found such gravitational waves which would fit to the cosmic strings. This is why the BBC writes that there's tentative evidence for string theory. What does any of this have to do with time travel? There is an old paper going back to the 1990s that says that if you align two cosmic strings the right way, then you can go back in time if you wind your way around them in the right way. This isn't as shocking as it may sound. In general relativity, time travel is indeed possible, at least mathematically. You can also do it with wormholes. It's not that the theory forbids time travel, it's just that we can't make sense of what it'd mean if we did it. By the way, this video comes with a quiz that helps you remember what we talked about. So what does all this mean now? First of all, string theory, strictly speaking, doesn't predict cosmic strings. Cosmic strings are what's called a phenomenological model. It means that you don't just take string theory, but make several assumptions on top of that, which may or may not be correct. Second, some physicists have argued that time travel around cosmic strings might not work due to quantum effects. And finally, the gravitational wave result from the pulsar timing array is at this point very tentative, and it could be many other things besides cosmic strings. In summary, the article from the BBC is not totally wrong. The discovery of cosmic strings would certainly lend support to string theory, and it would indeed bring up the question of time travel, but the evidence is so tentative, don't worry. Your future self won't come and complain you're spending too much time on YouTube, so don't forget to subscribe. Thanks for watching, see you tomorrow.